morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about problem solving on spatial filtering. So filters in frequency domain are low pass filters and high pass filters. So low pass filters that passes low frequencies used for smoothing or blurring of the image. High pass filters that process high frequencies used for sharpening of the image. And band pass filters are for spatial filters. So band pass filters in spatial domain. So the spatial filters used different masks, that is kernel, template or windows. There is a one-to-one correspondence between linear spatial filtering and filters in frequency domain. So in the frequency domain, filters are two types. High pass filter and low pass filter. So the low pass filters that passes low frequencies used for smoothing. So low frequency for smoothing or blurring of the image. High pass filters that passes for sharpening. So when we are going for the low pass and high pass filters, so low pass is for blurring, remove blurrings. It is for smoothing of the image. So in the low pass filter, blurring of the images, for when the images are blurring, then we need to use this one. High pass filters, when the images are, we need to go for the sharpening of the image. And band pass filters are for the spatial domain. So filters used different masks, kernel, template or windows. There is one-to-one correspondence between linear spatial filtering and filters in frequency domain. So filters in frequency domain and filters in spatial domain. So in the spatial filters are different and frequency domain filters are different. So we'll discuss those things. And spatial filters can be used for linear and non-linear filtering. Frequency domain filters just for linear filtering. The machines of spatial filtering consist of neighborhood or small rectangle and predefined operation that is performed on the image pixel. So already we know that the spatial filter can be used for linear filter. Spatial filters are linear filter, non-linear filter. And spatial filters are linear and non-linear filtering, and frequency domain filters are frequency domain filters are for only linear filtering. So there is nothing is there, only linear filtering is there. So the mechanics of spatial filtering. Spatial filter consists of neighborhood or small rectangle and the predefined operation of the performed on the image pixel. So the origins are there. So what are the origins are there? Suppose I am taking the one image. This is image is the x and y axis. Here also x axis and y axis of the image. So how many pixels are there? Means it is a 3x3 neighborhood of the pixel. Okay. So image of F spatial domain filter. Okay, it is one sample. X and Y are the coordinates, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 into 3 neighborhood pixels are there, and it is the origin. So when we are going for the filtering, creates a new pixel with coordinates equal to the coordinate of the center of the neighborhood and whose values as the result of the filtering operation. The operation performed on the image pixel is linear, then the filter is called a linear spatial filter. Otherwise, it is a non-linear. So in the previous figure presents the mechanics of linear spatial filtering with the 3x3 neighborhood. And the response output is the image in the sum of products of the filter coefficients and the image pixels values. Okay. So filtering creates a new pixel with coordinates equal to the coordinates of the center of the neighborhood. So any of the pixel I'm taking, the coordinates are there. What are the coordinates? Means x and y coordinates are there. So the center of the neighborhood and whose values are the result of the filtering operation. If the operation performed on the image pixel is linear, then the filter is called a linear. So operation performed on the image pixel is a linear, then the filter is called linear. So for if a linear operation, that is a linear filter. If it is a non-linear, then the mechanics of linear spatial filtering is a 3 by 3 matrix. I'm taking one example, 3 by 3 neighbor matrix. And the response, that is the output of the image, is the sum of products of the filtering coefficients and the image pixel values. So here g of x comma equal to w of minus 1 comma minus 1 into f of x minus 1 comma y minus 1 plus w of minus 1 comma 0 into f of x minus 1 comma y plus w of 0 0 f of x comma y plus w of 1 comma 1 f of x plus 1 comma y plus 1. So here g of x comma equal to output value. So output equal to input with filter. For the filter is applied to the input, that is the output. So output is a g of x and input I'm taking as a w, and f of x comma 1 is a filtering technique. So here suppose here I'm taking the center point. So here minus 1 comma minus 1, it is 0 comma 0 minus 1 comma 0 1 comma minus 1 comma 1. So it is the minus 1 comma 0 0 comma 0 1 comma 0 like this. Okay, minus 1 comma 1 minus 1 comma 0 0 0 1 1 so on. So this is the general mask size is a m into n, and the image size is x comma y. So here I'm taking one is the input, another one is a mask. So here we are assuming that the mask size is a m into n. So m equal to nothing but 2a comma 2a comma 2a plus 1 and n equal to 2b plus 1. Why? Because m comma m I'm taking as a mask size. And where a comma b are the positive integers, that is the odd filters. In general, linear spatial filtering of any image size is a m into n with a filter of small m into n is given by expression g of x comma y equal to summation of s equal to minus a to a and t equal to minus b to b w of s comma t into f of x plus s comma y plus t. Here x comma y are the each pixel and w visits the every pixel in f. So output g of x comma equal to input value with filtering value. So here one example, spatial correlation and convolution. Here I am taking, it is a matrix. Okay, so in this matrix it is a 3 by 3 mask, 3 by 3 mask, that is called filter mask. So everything filter mask is applied. Why I am applied the filter mask is for mask for filtering. So what are the coordinates? So I am taking the mask w of 0 comma 0. Here left side is 0 comma 1, 0 comma minus 1, minus 1 comma minus 1, minus 1 comma 0, minus 1 comma 1, 1 comma minus 1, 1 comma 0, 1 comma 1. And what are the filter coefficients? X minus 1 comma y minus 1, x minus 1 comma y, x minus 1 comma y plus 1. Here like this, minus 1 comma 1, minus 1, 1. Here 0, x plus 0, y plus 1, 1 comma minus 1, 1 minus 1, 1 0, 1 1. Okay, so the spatial correlation of the image, it is the image origin and image pixels with the mask is there. Here it is a mask size. Pixel coordinates. with pixel coordinates. So pixels of the image section under the filtering technique. So the correlation and convolution are very very important in the spatial filtering. So correlation is the process of moving a filter mask over the image and computing the sum of products at each location. And convolution is the same process as correlation, except the filter is first rotated by 180 degrees. So the process of moving a filter mask over the image and computing the sum of products at each location. So the process of moving a filter mask over the image and computing the sum of products at each location. Okay, so when we are going for the correlation or convolution, the process of moving a filter mask over the image and computing the sum of products at each location. And the convolution is that the same process as correlated, except that filter is first rotated by 180 degrees. It is same as correlation, but except the rotation of image is with 180 degrees. Here example 1, 1D illustration, assuming that f is a 1D function and w is a filter. Okay, here 1D filter is 1D image is there. We have to apply the 1D function with the w filter is applied to the image. So here 0, 0, 0, 1 all zeros are there. Here f equal to input and w equal to mask, and these are the origins are there. Here I am rotated the 180 degrees. Why? Because if it is a convolution process. So okay, the convolution process rotating by 180 degrees. So 2328 is there, 82321. So 82321. Why? Because we are converted the to the rotation of 180 degrees. Okay, when I am going for the zero padding, 12328. Okay, when we are rotating, this is converted to the 82321. 82321 reverse order. It is one reverse 82321. So 12328. It is a 82321. It is like this. Okay. So this zero padding, position after a shift, position after 4 shifts. So it is a final position. What are the inputs we can observe? 0001, 4 zeros are there. Here all 000 instead of zeros we are zeros are increased. Why? Because the positions are changed and 180 degrees is rotated. So 82328 and 12328. So the full correlation result is like this, and the full convolution result is like this. Why? Because 82321 it is 123 12328 12328 like this. Okay, when I going this one reverse order. So correlation and convolution. So correlation, one two three two eight 12328. So exactly a reverse order to the correlation, that is a convolution. And it is a 1D correlation of convolution of a vector with a discrete unit impulse. Note that it is a convolution and correlation function of displacement. It is one example of correlation and convolution with a given matrix with mask values. So to create the mask for the representation of 3x3 filter. Okay, the filter is there, but we have to apply the 3x3 mask for this one. So it is a 3x3 mask. What are the coordinates? What is the size? What are the parameters are there to create the mask of the filter for 3x3? So create the mask for the representation of 3x3 filter. Okay, so it is a 3x3 filter. We are applying the mask to that filter. How? It is a filtering mask. I am using the 1/9 example. So 1/9 means 3 square. So 111, 111, 11. If I am taking 1/16, that is the 2 power 4. 2 power 4 means here mid one is 4. So what are the surrounding values are there? Left, right, top, bottom. So these are the values are there. Surrounding values are 1. That means foreground is a black, foreground is a white, background is a black. So here The two 3 by 3 smoothing converging filters mask, the constant multiples are front, each mask is equal to 1 divided by the sum of the values of the coefficients and is required to the compare of its average value. So here the mask, the filter size is W1, W3, W4, W5, W6, W7, W8, W9. Okay. So these are the values are there. So for this 3 by 3 mask, I am using 1 by 9 of filter or 1 by 16 of this value. So if I am taking 1 by 16 means 1 by 2 power 4. So here the bit size is 4. So 1 by 9 means it is not a binary system. It is not possible. Though 7, then we are taking all ones are there. Okay. So it is, we are applied the mask with the 1 by 9 and 1 by 16. And next example, calculate the probabilities of different pixels, cumulative probability and rounded cumulative probability. So calculate the probabilities of there. They given the cumulative probabilities and rounded cumulative probabilities are there, but we have to calculate the probabilities for that one. Okay, here they given the pixel value from 0 to 7, that is a 8 bit is there. So number of pixels are there. What are the number of pixels? Okay, for each pixel value, number of pixels. So already probability values are given. How we got this one? We can check also. These are the cumulative probabilities and round to near to the 1 by 7. Hence the transfer function becomes input pixel value and output pixel value. So what are the input pixel values? 0 to 7. Output pixel values. These are the randomly I am taking 1, 3, 4, 6, 6, 6, 7, 7, 7. How it is we are now we are getting this one. Okay. So already the cumulative is there and rounded cumulative probabilities are there. So what we have to do? Just we have to find out the probabilities of there. So number of pixels are 7. That is I am taking as a 1 by 7 into probability values are there. So what are the cumulative probabilities? 0.187 and 0.147. So what are the values? We have to find out. The value is the probability value. It is the probability value. So another example, consider the two images subsets S1 and S2 shown in the following figure. For V equal to 1, determine whether these two subsets are 4 adjacent, 8 adjacent and M adjacent. So I am taking here S1 and S2, two matrices are there. So here, what are the final M adjacents or N adjacents? So S1, S2 shown in the figure. V equal to 1 determines whether the two subsets are there. So subset 1 and the subset 2, 4 adjacent and 8 adjacent of the and M adjacent. So if I am taking, this one, how many adjacents are there? It is a 4 adjacent, or say 4 means 2 power equal to 4 adjacent. 4 adjacent means 2 power 4 equal to 16. 2 power 8 adjacent means 256 values are there. Okay. So here I am taking the 4 adjacent. That means if I am taking the what is the middle. So how many adjacent values are there? 4 adjacent and 8 adjacent, M adjacent. If I am taking, these are the neighboring values. For the adjacent values, they are the neighboring values. If I am taking, it is a x plus 1 comma y or x minus 1 comma y, x comma y plus 1, x comma y minus 1, x plus 1 comma y plus 1, x plus 1 comma y minus 1, x minus 1 comma y plus 1, x plus 1 comma y minus 1, y plus 1. So how many adjacents are there? If I am taking 8 adjacent, it is a 8 adjacent value with the coordinates are x comma y. So it is a 4 adjacent and adjacent 8 adjacent are like this only. Here why I am taking v equal to 1 means what are the adjacent values are there? I am taking 1. If those are not adjacent values, I am taking as a zeros. Okay. So improved method, smoothing and sharpening, or smoothing and histogram methods I am taking. Here in the example, smoothing or sharpening what it may be. But in the smoothing technique why I am using means smoothing for high pass filters. For high pass filters, I'm using smoothing technique. So if I'm using the smoothing method, what are the issues are there? Noise with salt and pepper with 0.01 parameter is added to the original image in order to create a noisy image. So before the improvement, it is after the improvement. So before and after, what we done means I applied the filter process and mask technique. I have applied the filter, that means mask is applied. So read the image and convert the image into grayscales and convolution the grayscale image with the mask. What is the mask says here? 1 by 9, 1 by 9, 1 by 9. So what is that means? 1 by 9 of 1 by 9 of this matrix. Okay. So the matrix like this. If I am taking 1 by 16, then only adjacent values are taking values, remaining all zeros. Okay. So remaining all ones. It is a 1 by 16. So here also, if I am going for the smoothing method, salt and pepper noise is occurred, that is a 0.0 parameter is added to the original image. So it is a before improvement and after improvement, read image and convert the image into grayscale, convolution the grayscale image with a mask 1 by 9 and denoising the image will be the result of step 2. In the next step 2 we will discuss denoising the image. So noise and denoise. When I am getting the denoise means when I am using the filters, noisy, after the noise, denoisy. So histogram equation is nothing but a gray level distribution to centralized, and it is a histogram process. So histogram process means what are the applications? So what are the parameters are there? Suppose I am taking here, what are the parameters you applied? Say it is a before and it is a after. So before and after the matrix. So smoothing and the histogram. Histogram is nothing but it is showing the shape, background, and what is the color it will be showing in the histogram. Okay. So what are the filters applied? Which here smoothing is applied and it is the output. Then I am going for the histogram process. That is a gray level distribution is there. Okay. And we are going for this one today. The spatial filters is there in the filterings in the frequency domain. Low pass filter and high pass filters are there. Low pass filters are the smoothing or blurring the information. So high pass filters is nothing but a sharpening. So low pass filters are for the smoothing and high pass filters are for the sharpening of the image. And the band pass filters are the spatial domain. Spatial filters used for different masks. That is a kernel template windows. These are using different types of masks are using. And this is a one-to-one correspondence between the linear spatial filter and the filter with the frequency domain. When I'm going for the spatial filter, it is can be used in linear and non-linear. But in the frequency domain filter, only linear filter is possible. What are the mechanics of spatial filtering is nothing but a neighborhood or small rectangle, and predefined operation is performed on the image pixel. So spatial filtering are two types, linear and non-linear, but frequency filter is only linear. There is no non-linear. So it is a 3 by 3 matrix, that is a 3 by 3 neighbors of x and y coordinates with f spatial domain. So filtering creates a new pixel with coordinates equal to the coordinates of the center of the neighborhood and whose values is the result of the filtering operation. And the operation performed on the image pixel is linear, then the filter is called a linear spatial filter. Otherwise, this filter is a non-linear, and it is represents the mechanics of linear spatial filtering using 3 by 3 neighbor. And the output of the image is the sum of products of the filter coefficients and the image pixel values. So g of x comma y equal to what are the coordinates are there here? g of x comma equal to w of 0 comma 0. We can see here what are the values are there. It will be showing in this figure. W of 0 comma 0, left side is a 0 comma minus 1, 0 comma 1, 1 comma minus 1, 1 comma 0, 1 comma 1, minus 1 comma minus 1, minus 1 comma 0, minus 1 comma 1. Like this, these are the filter mask with image coordinates are there. So what are the correlation and correlation? So correlation is the process of moving a filter mask over the image and computing the sum of products at each location. And conversion is the same process of correlation except that the filter is rotated by 180 degrees. Okay, it is a 1D filter with W is a filter, and we are applied the correlation and convolution of that. It is the creating the mask to the following filter 3 by 3. So in the 3 by 3 matrix, I am applying the filter. So what are the parameters means? If I am taking 1 by 9, what is the matrix? If I am taking 1 by 16, what is the matrix? So here we are calculating the probabilities. The given values are cumulative probability and rounded cumulative probability values. Here S1, S2, the images are subsets are there. So we have to find out the 4 adjacency and 8 adjacent and M adjacencies. Here, if I am using the smoothing technique, what is the noise is there? The noise is a salt and pepper noise is there. And what is the process means? Read the image and convert image into a grayscale, and convolution of the grayscale image with a mask of 1 by 9. And if I am going for the histogram, gray level distribution to the centralized. That is a technique for the improvement of method of the image. Okay. And if you are going for the hit or miss transform in the general binary morphological operation, that can be used to look for particular patterns of foreground and background pixels in an image. Actually, the basic operation of the binary morphological, almost all the binary morphological operators can be derived from it. Hit or miss transform is an operation that detects a given configuration in a binary image using the morphological erosion operator and is a pair of disjointed structuring elements. Then the result of hit or miss transform is the set of positions where the first structural element fits the foreground and the input image, and the second structuring element faces it compulsory. So morphological operations are so these are the morphological operations. Today I am discussing about hit or miss transform. So hit or miss transform is an operation that detects a given configuration of a binary image using the morphological erosion operation of the pair disjoint structuring elements. The hit or miss transform is the set of positions where the first structuring element fits of the foreground of the input image and the second structuring element misses it completely. The structuring element used in the hit and miss is a slight extension to the type that has been introduced of the erosion and dilation. In that it can contain both foreground and background pixels than just foreground pixels, that is both ones and zeros. And the simpler type of structuring element used with erosion and dilation of a depicted containing both ones and zeros. So 1 and zeros are there. If don't care means what will happen means don't care means we don't know, no values can be taken. So don't care is nothing but a blank. These are the blanks are there. That means don't care. It is a white, black. So it is a foreground or object. And 0 is the don't care conditions. So here 4 different rotations of there. Here what are the ones are there? Here like this. Here the ones are like this. So 4 structuring element used to corner finding of the binary images using the hit and miss transform, and they are really the same element but rotated by different amounts. Here the hit and miss operation is performed in much same way as the morphological operators. Already we know that the morphological operators means there are 5 types are there. In that hit or miss transform is a one type of operator with a structural element also needed for this one. So structure element is a point of the image and comparing the structure element with the underlying image pixels. So if the foreground and background pixels in the structuring element exactly match foreground and background pixels in the image, then the pixel underneath of the origin of the structuring element is set to the foreground color. If it is does not match, then the pixel is set to the background color. For instance, structuring element is shown as used to find the right angle of the convex corner point of the image. If the pixels element from the shape of a bottom left convex corner, we are assuming that the origin of the element is in center of 3 by 3 element. So in order to find all the corners in a binary, we need to run the hit or miss transform 4 times with the 4 different elements corresponding to 4 kinds of right angle corner found in binary images. And here the figure 1 or above figure shows the 4 different elements used in the operation. So hit or miss transform is an image of A and B denoted by A into B. So B is a pair of structuring element and B equal to B1 into B1 comma B2. So B1 is an object and B2 is the B1 is an object and B2 is the background. So A to B and A hit to B is A minus B with A complement of B1 to B2. This transform is useful for locating all pixels configurations that match the B1 structure and no one doesn't match the B2 structure. Then the hit and miss transform is used for shape detection. It is one example of a hit or miss transform to identify the locations of the following shape pixel configuration in the image below using the 2 structuring elements B1 and B2. Okay, it is a sharper of image. Here input image. Here B1 is that is the object. Here B2 is there, that is the B2 is nothing but here no object or foreground you have taken. Here B2 is that what background. So B1 equal to object and B2 equal to foreground. Foreground is nothing but there is nothing is there. Object means we have to take the one. Okay, it is a hit B, A complement, A erosion B and A complement with B2. It is a before the input of the binary image and it is a hit or miss transform. That means what are the black unnecessary white are there, we are converted to the black. So therefore the hit or miss transform comprising of 3 steps. Erode image A with structuring element B1, erode the complement of A complement that is B2, and we are adding B1 and B2 and operation and equal to B1 into B2. So that is one thing. So here structural elements left to right. Left is the hit, middle and miss is the right final command. In this case, we are looking for a pattern in which the central pixel belong into the background while the north, south, east and west pixels belong into the foreground. And the rest of the pixels in the neighborhood can be kind of, we don't care about this one. Okay, when we are going for the, it is a background, foreground, it is a don't care for the condition. Okay, so when I don't want means I am converting to black. So converted to 0. When it is white means the pixel size is 255. When it is 255, it is a white. When it is 0, it is a when it is 0, it is a black. So here majority of 255s are there. That means object is very high. Here object is reduced. Size is reduced. But that means all the pixels are converted to 0 of unnecessary objects. and it is an example of T-shaped condition. Here I need a T-shape. Here I need a T-shape. But what here means 0 zeros are here I am converting to the don't care condition. Here also input is there. Input is the object. So this object only one object is there. So remaining all what was happened means remaining all I converted to the black. So what are the terminologies in morphological image processing? All morphological processing operations are based on the mentioned terms. Structuring element. It is a matrix or a small sized template that is used to traverse an image. The structuring element is positioned at all possible locations in the image and it is compared with the corrected pixels. It can be of any shape. Here fit, hit, miss, three types are there. Fit means when the pixels of the structuring element cover the pixels of the object, that is fit. Okay, when I'm taking the image, it will be fit. Suppose my mask is 111, 111. Okay, it is fit structural element. It is fit means all are mapped. Hit means anything partially mapped. At least one of the pixel structural element covers the pixel. That is a hit. And miss means there is no matches of the input pixel to the mask. That is the miss rate or no pixels are there. It is a original image dilation and it is a erosion. After the dilation, it is erosion. After the erosion, it is a dilation. So what is the finally I got closing and opening condition. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.